So let's start the second half of the morning session with Matteo that will talk about the numerical model of extreme core collapse.
Thank you, Olivier. Can you hear me well from behind? Okay, great. So thank you, first of all, to the organizers for this wonderful workshop so far. I'm learning lots of things. It's very nice to sort of have the community, multi-messenger community, talking to each other and sharing the latest efforts in the understanding how extreme events, multi-messenger events work. So I will continue through this line of talks, focus mostly on numerical models, theoretical models, trying to understand the underlying physics of extreme events. Contrary to what you've heard so far, which was mostly focused on neutron star mergers, compact object mergers, I will focus specifically on the other source channel of these extreme events, which are core collapse supernovae, specifically extreme core collapse supernovae, very energetic events. And more specifically, the efforts to, as a community of modelers, to sort of try to establish the level of agreement of our sophisticated models. There is lots of physics within, and it's important to sort of take everybody's work and try to understand where we're at and what we need to do to improve our models. So these are, you can see all the list of collaborators that are involved in this ongoing project, comparison project. And so first thing first, just a bit of context of the physics. So we're talking about core collapse supernovae, so the end of life of massive stars having more than typically 8 solar masses, which are one of the main channels to the formation of new compact objects, neutron star black holes. We know that these events are extremely energetic. They provide dynamical feedback in the host galaxies when they occur, and they are therefore also very efficient particle accelerators. So there's lots of energy that particles can take from the system, can be accelerated, and therefore provide a whole plethora of high energy and non-thermal emissions on all wavelengths. There are the poster child events for the multi-messenger emission of signals. We have, so they are sources of gravitational waves, neutrinos. In fact, the first multi-messenger detection was supernova 1987A, which was the combined detection of neutrinos and photons. And last but not least, as we heard from Daniel, these are systems where explosive nucleosynthesis allows the production of heavy elements that stellar nucleosynthesis cannot hope to achieve. And therefore, they are a crucial step into the evolution of galaxies and the universe as a whole. We know that in terms of energy, the majority of the energy of core collapse supernovae is essentially lost. Thanks. in neutrinos, 99% of that bulk of budget, 10 to the 53 ergs, is basically lost in neutrinos. Just 1% goes into the ejecta, and a tiny fraction of that goes into gravitational waves. But in terms of information, we know that gravitational waves and neutrinos are quite complementary messengers. So, but neutrinos, they're not just taking away a bulk of the energy, but they also play a fundamental role when it comes to making the star explode, because we know that the vast majority of core collapse supernovae happen because of the so-called neutrino heating mechanism. That means that a small fraction of the neutrinos which are produced due to the ongoing accretion onto the proton-neutron star that emit it, they decouple from the proton-neutron star, but they deposit some energy behind the shock that would otherwise stall. And that injection of energy drives turbulence, convection, and gives the extra push to the shock to actually make the star explode. So this is, let's say, the 99% of the cases, but these are the regular cases where neutrinos do the heavy lifting and the energies are sort of a regular standard. But what it comes to when we have sources such as hypernovae, long gamma ray burst, supernovae, all these sources that exhibit exceedingly high either kinetic energies or luminosities, or for instance, plateaus in the X-ray light curve. These are all sources where neutrino heating mechanism just doesn't provide enough physics to account for that kind of energetics. And so we know that we expect the combination of two main ingredients, fast rotation and large-scale magnetic fields, to be at play and to essentially provide the extra energy budget to make the extreme event occur. And rotation is essentially the energy reservoir, the extra energy that you need to power up the sources, and large-scale magnetic fields are required because otherwise there is it's quite tricky to extract that rotation. So you have to tap into the rotational energy by slowing down through magnetic stresses the central compact object. And this is something that we have been able to reproduce through the years with these extreme jet simulations. And of course, as I mentioned, magnetic fields are fundamental ingredient, and their origin is still, as we heard from Alexei, a matter of study and sometimes debate. The origin can be, there are several suggestions. So origins that go trace down to the progenitor star, maybe something that has to do with a previous stellar merger that has amplified the magnetic fields, or proton-neutron star dynamos. So dynamos that amplify the magnetic fields within the time scale of the explosion itself, and then can sort of produce and allow the explosion. So, but regardless of the origin of the magnetic field, we know that the dynamics of magnetic field and rotation is fundamental to understand how the explosion occurs, but also to explain, for instance, what is the outcome of the explosion in terms, for instance, of production of heavy elements, the nucleosynthesis. Here you see a plot of nucleosynthetic yields of heavy elements produced with calculation based on core collapse supernova models of very energetic events with strong rotation magnetic fields. And one thing that pops out is the fact that you have quite some difference in terms of the ability of the models to reproduce. For instance, the first peak is pretty common for magnetized models. The second peak is something that we observe only when we have a strong dipolar aligned magnetic field, so a very specific configuration. And the third peak is something that these models, at least in the first second or so of the explosion, really struggle to do. And so we are starting to understand that the dynamics of the accretion, the transport of angular momentum, and the ejection of neutron-rich matter is something that crucially impacts the yields. And essentially, we need to understand how these, the details of how this happens. And so there was a question about the impact of nuclear astrophysics, nuclear physics parameters that come into play in this calculation. So when it comes to the vastly unknown or uncertain masses of the neutron-rich nuclei and then decay, or when it comes to the beta decay reaction rates, structural reactions, these are all ingredients that are inside the nucleosynthetic calculation, so sort of under the carpet. And one may ask themselves, well, what happens when we take into account the uncertainties? And when it comes down to these yields, what we saw is that by far the largest uncertainty comes from the dynamical modeling of the magnetic fields and the mass itself. So when we play with these parameters, these curves do not change that much. But when we just change the distribution of magnetic field, it changes a lot. And so that means the explosion efficiency directly affects these results. So we need to get the dynamics right. And so this is essentially something that a difficulty, uncertainties that stem from the vast landscape of possible, so the combination of initial conditions that we need to take into account. So we start with some progenitor and having some core mass, some degree of mixing, some degree of mass loss during its life, which are already quite uncertain. And then we need to take into account and sort of make a guess in terms of what's the rotation rate, what's its profile at the moment of collapse, which is again very uncertain. Then magnetic fields. How does the dynamo evolve over the course of hundreds of millions of years or billions of years in a 1.5 dimensional model of a star? That's quite tricky to get right. And so we also have uncertainties in the pre-collapse dynamics. What are the perturbations? What does the star look like the moment where it starts collapsing? All these affects the outcome of the explosion. But on top of that, then we need to decide what are our tools to model this explosion. We need to decide in which way to treat gravity. So either go full GR, and that sort of puts some constraints in the amount of time that you can follow your model, or you can have some more approximated pseudo-Newtonian treatment of the potential, and that sort of has some shortcomings. Then you need to have neutrino treatment. This is not an optional. So you need to be able to trace the interaction between neutrino and matter, and the accuracy with which you do that can have a direct impact on the dynamics, specifically for regular core collapse supernovae, but also on the nucleosynthesis for sure. And then you need to take into account, for instance, nuclear equational states. So this is where nuclear physics brings, once again, some uncertainties because we don't really know exactly how matter at those densities behave, but we need to take that into account because a different degree of softness, different degree of how compact your proton neutron star can be, that has direct impact on the size of the proton neutron star, its temperature, the amount of winding that you can have. All these sort of things sort of contribute at some point or another to the dynamic of the explosion. And then there is a third column, which is the numerics. So this is something that needs to be there. You have to make a choice in terms of the geometry of a grid, to make a choice in terms of the refinement, sort of to make things happen on human time scale, and also the things that you need to take care of. And typically, groups don't talk too much in terms of setting up standards. And this is why there has to be a need to do some quick comparison, to start to sort of compare and see where we are at. So there have been some quick comparison in the recent years. I will just breeze through it. We can discuss this later. So in terms of regular quick-collapse supernovae, we know that the agreement is not too bad. We know that there are some deviations in terms of the neutrino helium efficiency, but these are something that goes along the line of, let's say, a few percent or almost 10%, and something that has been solidly and robustly assessed. But when it comes to rotational, multi-rotational models, we see that the deviations are quite larger. We have this here, a comparison of 2D models, and already we have some quantitative deviations between two different codes, which allegedly should have the same initial, well, allegedly, they have as much as possible the same initial conditions, but they struggle to have the similar results. And all comes down essentially to the way the angular momentum is transported. That is the main ingredient that then dictates how the explosion behaves. So these are 2D models. The objective of the study I'm going to show you is to go 3D and to add more models and sort of try to make a more solid statement as to how quick-collapse models are performing nowadays. So these are the codes that we so far have included in the project. There are maybe some of you, mostly none of you actually, will know that, but these are some of the state-of-the-art codes used to perform the gravitational collapse of stars in all kinds of regime. But in this case, we are considering fast-rotating, highly magnetized models, which are essentially the progenitors of long gamma-ray bursts. So there are different grid geometries, neutrino treatments, and dimensionalities. And we use, of course, the same nuclear equational state. And we also included some non-asymmetric perturbations because we know that those perturbations affect the explosion efficiency right from the get-go, and also can leave a signature in the multi-messenger signals that we can produce. So in terms of initial conditions, we have a pretty standard progenitor of 20 solar masses at zero age main sequence. We have a standard analytical rotation profile, which is a very fast rotating core, 1,000 kilometers, and then constant angular momentum profile, and then a aligned dipolar magnetic field. So as simple as a standard as you can get. The results show us that there is quite some spread in terms of the expansion of the shock already in the first 50 milliseconds. So we have the same models that some of them are pretty fast in expanding the shock. So all of them explode, but to very different degrees. We have the Enno-Salkar code, the 2D and 3D models, which are the fastest, and the slowest are the model produced by the Japanese group, the 3D NSE IDSA, which has a different neutrino mechanism, neutrino treatment. In terms of energy of the ejecta, we have the trend is very similar between different codes, but there's an offset in terms of the onset of the actual increase of the energy. And as you can see, the simulations are just too short now to say something about the actual final energy of the explosion. But the trend is very similar. Quantitatively, we had the same explosion. Quantitatively, this is a bit more tricky. So these are a couple of animations showing on top the distribution on a meridional plane of the ratio of magnetic to gas pressure. So this tells you how much dominated by magnetic fields the fluid is. And on the bottom, we have the specific entropy. And this is done for two codes, Flash and Alcar, and in here you have a 2D realization of that. And if we start, you see that this is the shock at the beginning, and then you have these ejecta. They start drilling through the star. You can see already that Flash is sort of lagging behind, or rather Alcar is just shooting out. Very axisymmetric despite being 3D. And despite this having a larger magnetic pressure, we still have a much more collimated, much faster outflow coming from the model that was the faster in the shock expansion. And if we zoom in into the animation, we see that already at the base of the outflow, we have in Flash some wobbling, so some non-axisymmetric modes being excited, whereas for Alcar, this is not really the case. So we think that this is mostly a matter of resolution of this model being a bit too poor to capture this. But this is something that quantitatively tells us that we are not on the same level with respect to these two models. But we need to go we are trying to wait for some extra data to assess where we should look at in terms of convergence. If we look at the particle neutron star, I mean, diagnostics are pretty close in terms of the mass of particle neutron star. In terms of the moment of inertia, there is some outlier, which is the Flash code. But this is, again, a feature that is mostly due to the resolution. So by having an enhanced resolution, which comes very expensively, this curve tends to then overlap to the others. If we look at the kinetic energy of the particle neutron star, some codes are clustering, others instead have a different degree of rotation. And this is telling us that some codes don't track rotation within the particle neutron star the same way. And this is probably related to the fact that some codes they carve a spherical shell within the center just to allow for an integration which is practical, instead of having maybe some multidimensional description of the interior with some coordinate scheme. Just a quick couple of slides in terms of neutrino gravitational wave emission. We're starting to do some analysis on these models, and you can see these are light curves along the equator for electron neutrinos, antineutrinos, and heavy lepton neutrinos. And you can see there is a sort of this outlier in the coconut code, which uses a different neutrino treatment, the fast multigroup transport approximation. So it is not too surprising that there is some differences here, whereas for Flash and Alcar, we are pretty much in agreement. For electron antineutrino, there is a bigger spread. And this is something but there is some overlap as well. And we know that this phase is quite important when it comes to characterizing the accretion phase of matter on top of the neutron star and the emission of neutrinos. And for heavy lepton neutrinos, something along those lines with a rapid decay of, again, the coconut. And for gravitational waves, this is an example of the strain along the A plus and A cross polarization along the equator. And we see that this is the bounce signal, very axisymmetric just due to rotation, which is relatively similar. And then we have this memory signal that starts arising. We do expect this due to the asymmetry of ejecta, this kind of signal. And it's, once again, there is an offset because our explosions are not right on top, but there is some delay due to the different efficiency. And we're starting now to collecting more data. This is an attempt of having a spectrogram, which is a very short time window. This is frequency against time with a conveniently unreadable labels. But essentially, between Enos and Alcar, we have some features that do not really overlap. We have an excess of power where in Flash this is not the case. So we still have some work to characterize it. I'll leave you with my conclusions. And in terms of goal, we're trying to refine our analysis, collect more data. But this just showcases the need to do this in a more systematic way in sort of to provide an improvement of our models and ultimately some more robust prediction for observations. Thank you for your attention.
Thank you, Matteo, for this nice talk. Is there any question for Matteo?
Thank you. Very nice talk and very nice work. I was wondering, since you mentioned the kink instability in this comparison between the Alcar code and the Cartesian Flash code in terms of seeing these instabilities. And so I was wondering, have you checked? So it seems like the expansion speeds are also somewhat different, right? And so that's a critical. Have you compared those, because that's like critical in determining, you know, how much time does the kink instability actually have to grow? And so, you know, there could be intrinsic physical differences between the scenarios in terms of, you know, neutrinos, neutrino absorption, but also, you know, colloidal to toroidal magnetic field strength in setting, like, you know, what the jet power and expansion speed is, because that then determines whether the kink instability can develop or not. So maybe it's not just a resolution. So bottom line, maybe it's not just resolution, but also like different physics, right?
Yeah, absolutely. The point is that having that kind of different propagation of the shock might still be somewhat dependent on the amount of dissipation that you have, because if you have more dissipation or less dissipation, that kind of affects also the amount of magnetic pressure that you're able to build up. And but it's true that resolution is something that just can guide us in terms of assessing to what extent we are converging toward the results. But one other possible reason for this difference is that there is some intrinsic sort of difficulty due to the discretization in terms of a spherical and a Cartesian grid. So we are open to the possibility that maybe there is something going on in that department that maybe we need to take into account more, and maybe there's something even trickier to resolve. But for definitely, that for sure, we need to take a look into what suggests as well. Yeah.
Thanks again.